one of the primary uses of a Taylor series is that you can replace the transcendental function. Transcendental meaning non-algebraic, meaning it's not polynomialish in nature. So the e's or the logs or the trig functions, they are equal to an infinite polynomial. So we hopefully all remember, or at least we've worked with, the power series for the cosine. It doesn't come up very clear on the board, but you have this thing in front of you here. I think I'm going to try to zoom in a little bit more because that's still, it's a little bit small. Now, will this autofocus? I'm trying to zoom in, but it's really not. Oh, maybe I should do auto. This just looks scary, the sequence of things here. What we have, first of all, on your sheet, I have the power series for the cosine, which either you've derived or you just simply use. And the best thing we love, and what I like to do in my class, I like to do things formally. If the cosine of x is this thing right here, okay? If this is the cosine of x, you guys know what I like to do, then what is the cosine of thing? If the cosine of x converges for all values of x, then cosine of x will converge for any function I put in there as long as the function itself is continuous. So I could replace this with x to a power. I could replace this with an entire other function if I wanted. So if I replace x with thing, all I'm doing is replacing that x with thing. So the original question is cosine of x squared. So the power series would be to replace this like this. Well, that's easy. I now have a power series. Well, it's still an infinite number of terms. But I can integrate a power series because a power series is nothing more than a polynomial. And remember the rule, and we've done this before. The integral of the summation is the summation of the integrals. So I'm actually only integrating one term. I'm integrating the nth term, and then I'm expressing my answer as a summation. So if you look on there, I have the integral equals the integral of the sum, which is the sum of the integrals, and then I integrate one term at a time, and I asked you to go from 0, in this case, to 0.2. And so you ask, well, how valid is this? I have an infinite sum. Well, what I did, if you can see, I expanded the first few terms. Notice, okay, that's n equals 0, n equal 1, n equal 2. By the time I got to n equal 3, do you notice anything about my denominator? Let's see, millions, billions, it's over 11 trillion. With a numerator of 1. That's pretty small. If something converges as an absolute guarantee, it means your terms are getting really small, really fast. And when we studied the remainder theorem, it says basically all the rest of the terms combined will be smaller than the size of the next term. Well, I have a term there that's 1 over, right, 10 to the 13th power, roughly. So that means I have accuracy. So I actually checked this, I calculated. Even Wolfram couldn't get this accurate. I gave you, let's see, how many decimals did I give you? 1, 2, 3, I gave you a bunch. I actually calculated it longer. We went 4 terms, and we are guaranteed at least the first 13 decimal places are correct after 4 terms. Imagine if we used a computer and did a loop and maybe did 50 to 100 terms. We might have 1,000 decimal places. We have way more accuracy than we'd ever need. I cannot tell you what the antiderivative of the cosine of x squared is as a closed form, as a single function. But I can evaluate the integral to any degree of accuracy. Now, what we want to consider is what does the graph actually look like? Because what is it we just found? Because this is all about asymptotic nature and asymptotic convergence. We have a cosine function, in this case a weird cosine function, and I'm saying it is equal to an infinite polynomial. But how does that match in terms of calculation? So what I want to do here is, turn this back on again, it keeps turning off on me. Okay, so what I did was, I took our power series that you have right in front of you, and I simply did, you know, I'm still not happy with how this looks. I just expanded the first 4 terms. So the power series you have in front of you, I just took the first 4 terms. I took n equals 0, n equal 1, n equal 2, n equal 3. And if you can't see it, it says x plus x to the 4th over 4 plus x to the 7th over 14 plus x to the 10th over 60. That's the power series you have right in front of you. I just did the first few terms. Then I changed my window because I'm only asking you to evaluate from 0 to 0.2. So I just made my window really small. I went 0 to 1 in the x direction, and I think negative 1 to 1 in the y direction. And now I've graphed both functions. Again, I have, this is not very good. Oh boy. Okay, let me just, Graham, I'm going to use for you for a minute. Can you, I need to blow up that screen about 4-fold. And you can see it barely, I know, from here, right? But oh, you know what? I'm sorry. I'm sorry, I jumped ahead a little bit. This is the next problem. Oh, my bad. That's why that looks funny. This is the next problem on the next page. Okay, we'll hold off on this one for a minute. I just want to be able to see it. So what we've got is a polynomial, a transcendental function, that as long as I'm close to 0, because I'm expanding, I won't be able to tell the difference. The naked eye, they look exactly the same. So from a calculation standpoint, we'll get essentially the same thing. So I want to flip the page over now, because this is the next one I have on. I can't do them all efficiently on my graphing calculator quickly. So now we're doing the e to the x cubed, which again, that does not have a closed form. You cannot integrate that term. No amount of substitution will give you, and it equals the following function. So we change it to the power series first of all. And we use the one for e, which is probably our favorite one, right? 1 over n factorial x to the n. Then from there, I replace the x with x cubed. Okay? And so now we get this really icky looking power series. We integrate the power series. We do the exact same thing we did before. The antiderivative of the power series, again, is just a polynomial. No matter how we look at it, it's a polynomial. So what I want to do in this case, like we did before, because e to the x is this, okay, we know this is e to the x. Therefore, e to the thing, I just replace x with thing. So that's e to the 3n. If I want to integrate this whole thing, I can. I just integrate the nth term and I set up the new sum. But for practicality's sake, if I said, what does this actually look like as a graph? Can you graph an infinite polynomial? No. But can you graph the first few terms? Yeah. And what's happening is, these coefficients generally are getting really small really fast. So the contribution of the remaining terms is disappearing very, very quickly. They're almost becoming transient terms in that sense. Because, you know, by the time I get to n equal 10, right, it's 1 over a million. Really, really small contribution. So if I only grab the first few terms, I know that I'm asymptotic to that. So in this problem here, let's walk through it. I said integrate in general. This is the Taylor series. If I only take the first few terms, we call that the Taylor polynomial. So when I evaluate this, if you're looking down at your page, I did 0, 1, 2, 3, 4, 5. I went to n equal 5. And once again, the numerical value we got was accurate to 9 places. So if I want more accuracy, I go more terms. But this time, I actually want to compare, because e to the x cubed, if I had to graph it, would be very, very difficult, right? Try to take derivatives and do, that would be kind of nasty, so I cheat and use my titanium here. So what I did in this case is I just went the first few terms. I was looking at the other one originally. I went just the first few terms. Okay, now, Ram, I need you again now. Give me a way zoom in on this one. There we go. Can you guys see that? Mm-hmm. E to the x cubed, and then I just took the first few terms of our power series. I didn't even go 5 terms. I wanted to fit on the screen. Is that sharp enough back there? It's not very good from where I'm standing. So I've got x, x to the 4th over 4, x to the 7th over 14, x to the 10th over 60. Now what I did was I chose a window that was fairly small because I'm only asking you to integrate from 0 to 0.2. So then I said, let's graph both functions on the same set of axes. Here is why this stuff is so cool. When I did both graphs, the naked eye can't tell the difference. Now there's no way you can tell me a 10th degree polynomial is equal to e to the x cubed. Right? One's a polynomial, one's transcendental. But as long as I'm close to 0. Now, you're saying, well, okay, how do I know that you even have 2 graphs on here? You know, I could have been cheating. So let's go back to a window. I'm going to show you. I'm just going to change that from -1. I'm going to change one thing only. Right? I just changed x min to -1. That's all I changed. What happens is they meet up and then they write each other. Now, what does that mean when we say they meet up and they write each other? Well, asymptotic convergence means, in simple English, what? Convergence means what? The difference between them approaches 0. Just moving back to home. The difference between them approaches 0, and they become equal based on a limit. Okay? I don't need them to be equal. I just need them to be so close that I can't distinguish the difference between them. Will this work all the time? If I have a transcendental function, a log, an exponential, an inverse trig, sine and cosine, things that we know a power series for, then you can integrate anything that uses that and an argument that is continuous. It has to be continuous and defined. For example, if I said 1 over x instead of x, would that present a problem perhaps? Well, 1 over x is not defined at 0, and we're expanding this thing about 0. Might that be a problem? Yeah. If I replace x with 1 over x, it's no longer polynomial. So there are certain rules that I have to maintain. I still need it to be a polynomial. I still need it to be continuous. I still need it to be able to, take derivatives and that sort of thing. So I can't do everything, but I can do most everything. Okay? So we looked at the first two things. Now, I want to give you a little bit of background. Some people forget some of the rules, particularly as they pertain to factorials. By the way, did anybody come in late and not get a handout? Anybody else? Okay. You want to be able to follow along at home here. And I will be posting these on Blackboard because some people couldn't make it today who wanted to. Now, I want to do the next one. The next one's particularly icky because we're not going to use a Taylor series on the next one. The reason is we don't have a Taylor series already set up for the square root function, right? Because the square root function technically is algebraic, not transcendental. It involves polynomial-ish things, not sines, cosines, exponentials, and logs, things of that nature. So I want to do a power series of something really nasty like 1 plus x cubed. If I do a Taylor series, that means I got to take a lot of derivatives. After the first derivative, this is not fun. Because you start having multiple terms, you have product rules, you have quotient rules, you have chain rules. And by the way, remember I have to take over and over and over again until I see a clear identifiable pattern. Not our friend. But we have something called the binomial series, if you remember. This is one of those that goes in line with the binomial series. Now those in the calculus class right now, you know the binomial series is anything I can write of this form. Generally k is going to be an integer or something with halves. If k is a positive integer, this is just a simple polynomial, right? If k is 3, then I just have a cubic. So we're really thinking k being a negative integer, or a half, or a 3/2 or something. Now, what if that's not an x, but that's some function of x? Well, again, I tweak it. So if you remember, what does this look like? It's 1 plus kx over 1 factorial, if you remember, plus k minus 1 over 2 factorial, x squared, forever and ever and ever and ever. What did I do in this problem? I made my x into x cubed. So I just replaced all these x's with x cubes, and the k I chose was negative 1/2. Well, that makes this thing here really, really exciting, meaning really, really icky. So how am I supposed to do that? Because if I can't write this in a closed form, if I can't write it as a single summation, then it will be really hard to use. Plus dot, dot, dot doesn't work very well if you're doing this on a computer, does it? Right? If I'm trying to program something and I can't write a closed form, I can't actually enter the entire thing. So a simple little trick that we use with factorials, I'll re-remind you. Some of you have seen this recently, some of you saw it a long time ago, perhaps some of you didn't see this at all. If I said I have 2, 4, 6, up to 2n, that's the product of the first n positive even integers. So if n were 100, it's 2, 4, 6, 8, up to 200. Okay? I would like a closed form for that. Because if I had to do this on a calculator and n were large, that would take me forever. But it's not a factorial, is it? It's missing all the odd terms. But can I write it 2 times 1, 2 times 2, 2 times 3 up to 2 times n. Is that the same thing? And because multiplication is both commutative and associative, I can rearrange and regroup. So exactly how many 2's do I have in that product? N. And then I have 1, 2, 3, 4, up to n. So that's a really nice one. So the product of the first n positive even integers is, okay, so if you've never seen that one, that's handy because it means I don't need to write something in this form. I can write, or even that form, I can do this. This is not the one that shows up though. You're never going to have that one show up. The one that shows up are the odds. And the odds present a little more of a problem. So over here, I'm going to expand the odd ones because we have to use this on the next problem. So if I said 1, 3, 5, 7, up to 2n minus 1, now that's a product of the first n positive odd integers. You notice they're all 1 less than the evens. Well, no such trick of factoring out 2's, right? That's not going to work. So what was the trick we did to make this work? See, I really would like that to look like a factorial. What if I go 2, 4, 6, 8? What if I multiply that on the inside? Have I changed the value? Well, yeah. But what if I do this? I just multiplied numerator and denominator by 2468 over 2468. So have I changed the value overall? No. But what did I make the numerator? I made it into a factorial. In fact, very specifically, what factorial? 2n factorial, and the denominator is the product of the first n positive even integers, which we just figured out was 2 to the n in factorial. This will be true for any positive integer n. Okay? Now I won't go through, let's just try different numbers to see that it works. Those in the calculus class, we did that, you know that it works. The product of the first n positive evens is that, the product of the first n positive odds is this. A little more complicated, but this is the one that shows up far more often. So why does this one show up? Because the pattern created with fractional exponents. You would never have an exponent of 2 over 2. You'd have an exponent of 1 over 2 or 3 over 2 and so on. So the binomial pattern, when the binomial pattern has things like this in it, right? K, K minus 1, K minus 2 and so on. If K involves a half or 3 halves or 5 halves, what do you have? A sequence of odd halves, right? Let's say K was negative a half. That's what it is in our example. And the next term would be negative 3 halves, and then negative 5 halves, and so on. So how do I deal with negative a half, negative 3 halves, negative 5 halves, on and on and on? Well, I'd have negative 1, negative 1, negative 1. So clearly, if I did this n times, I'd have negative 1 to the n, wouldn't I? I also have my 1, 3, 5 pattern, and I have... Does that make sense? So the pattern created with the halves looks something like this, but we now know exactly what to do with that. We have it right here. So going back to the problem, I have to do that because not everybody knows this trick. If you don't know this, it's not possible to express your answer in a closed form, a summation of one thing. And most of the textbooks won't go that far. They'll just kind of leave the dot, dot, dot thing. So regardless of the numerical value, what I have here is that when I expand this using the binomial series, and I have the halves and so on, we see a clear recognizable pattern where my numerator is the 1, 3, 5 like I have over there, stopping at 2n minus 1. Then when I put everything together, I have an nth term. And that's the beauty. If I can describe the nth term, then I can describe the summation using that nth term, and I have a closed form. Closed form meaning I have a summation of exactly one thing. That I can program into technology, or that I can expand by hand if I just want the first few terms. Now to integrate that, that's kind of a beast. You have factorials in numerator and denominator, but remember, factorials you're not integrating. The factorials are constant, you're integrating the x. So you treat the factorials quite differently. So now I have some really big, icky, nasty integration in here. There's our original question. There's our power series. When I get all done, I get something big. And the beauty is I just used the first 4 terms in the expansion. The first 4 terms were 1/10, 2 over 160,000, 24 over 4,480,000,000, and the 4th term was 720 over 230 trillion, it looks like. That's the 4th term. So once again, I think we're converging really fast. And I have fun with this because even when I double check my calculations on Wolfram, it will give me 6 decimals. So I used my cheap $9 calculator to get 11 or more. Even my titanium won't give me that many unless I have to really be careful how I ask the question. But I double checked and not only are all the numbers correct, this calculation, again, the first 11 decimal places are accurate. It's actually accurate to more than 11, but the first 11 we know are accurate. And that's amazing accuracy. So you're working in physics, you're working in chemistry, where you might be using astronomically large numbers or infinitesimally small numbers, and you might need decimal accuracy, right? Chemistry, what type of decimal numbers do you typically have in chemistry? On the order of what? 10 to the negative 23rd, yeah, right? Molecular weight kind of stuff. So if you have numbers on that order, you need a lot of decimal places that are correct before you absolutely are certain. If you're talking about an astronomy class, and now you're talking about astronomical distances, right? You're dealing with things where it's 10 to a large power. But I don't like everything rounded off. I don't like to see numbers where I have some large exponent and then everything after that's a 0, knowing there are probably not very many zeros, because we don't have the ability to calculate or to control the decimal values. This is kind of a nice mix here. I can't give you the exact answer to the problem, but I can give you as much accuracy and as much precision as you want. So if you say I want 20 decimals, okay, let's go one more term. That's probably all we need is one more term to have 20, which is really incredible because we're doing this by hand. So if we have more technology available, it's really cool. This is one of the reasons I really like this stuff, is because we're using what we know about polynomials to make conclusions about things that aren't polynomials. All right? Now, if I use something like e to the x is a great one, right? E to the x is wonderful because we know e to the x has certain properties, and as long as I stay close to 0, it's really good. But what if I want to do a calculation of a number further from 0? You see, I'm doing integrals with 0 to small upper limit. What if I wanted my numerical values to be bigger? Is there a way of doing that? Going back to the previous problem here. I'll do it on this board. I've got something of this nature. I'm working with e to the x. And we're going to do an estimation problem. In a Calc 2 class, you'll do things like estimate, e to the 0.1. Well, if I use the power series for this, because it's expanded about 0, then it means I have a polynomial that's centered about 0, and the polynomial and the exponential function will look almost exactly the same around 0. But what if I change the question to estimate e to the 4.1? Do you think the polynomial is going to be as accurate now? Because this is going to be a large value. The polynomial won't be nearly as big because this is escaping. If I expand this about 0, this will not be very accurate. Do I have to expand about 0 though? Or could I expand about something else in general? Well, e only really works well if you expand about 0 because all your derivatives are e to the x. But other functions may be slightly different. The last problem that I want to look at, so go back to the other side of the page. I'm going to give you an example of where this works. We're going to do an estimation of the cube root of 1.2. And you say, why would I do an estimation? I have a calculator. I was at Mesa College before everybody had graphing calculators. I was at Mesa College before the internet. That is hard to believe. There was a time. I was at Mesa College before there was texting. Yes, there were automobiles, there was electricity, and there was running water. There were no calculators that had a square root key on them when I started at Mesa College, unless you were willing to spend a lot of money. And the graphing calculators that came out back then weren't very good and weren't very accurate. I need to do a calculation. Let's go back 50 years. Let's go back 400 years. I need to do a calculation, and no such technology exists, or quite simply, you are in a place where you actually don't have the ability to do the calculation directly. Is there mathematics that allow us to do estimations that are really, really close, like what we've been doing so far? Sure, that's the whole point of the Taylor series. Now, of course, you have a calculator in hand, but remember, I might have to integrate something that I can't find an antiderivative for. So having a calculator won't really help me. The calculator is great for the number crunching, but it won't necessarily answer the question for me. So I want to look at something like, I used the cube root function. Now the cube root function we really can't expand about 0, like we did with e and sine and cosine. Anybody know why? This goes back to the definition of the Taylor series. What does the Taylor series involve in the expansion? What are all of my coefficients? Aren't they derivatives? Derivatives evaluated wherever I'm expanding it about, which is usually 0. So what's the problem with the cube root function then? Well, if f of x equals x to the 1/3, what's wrong with 0? Cube root 0, 0. But the first derivative is 1/3 x to the negative 2/3, or 1/3. Oh, I can't expand that about 0. I can't evaluate that. In fact, every further derivative is going to have an x in the denominator, which means I can do no zeros. Okay? This is what it means to be analytic. To be analytic means you're infinitely differentiable at that value. This is not analytic at 0, but it is analytic at 1. That's why we choose 1. 1 is convenient. And besides, 1 makes it really easy to do calculations. So when we expand this guy, we expand him about 1. That's why my series, okay, that's why my series has x minus 1s. It's always x minus the number I'm expanding it about. Now, in this problem here, I did the entire problem, expanded about 1, because our calculation was cube root of 1.2. And you have the notes in front of you. You can look at that. What if I changed the question? What if I said, you know what, instead I want you to estimate the cube root of 8.1. I don't want the cube root of 1.2 anymore. I want the cube root of 8.1. Of course, we can take all of our derivatives and expand them about 1, and 1 is very convenient. But 1 is not very close to 8.1. So my estimation might not be very good. My curve, the cube root function, and the polynomial may be too far apart. Any brilliant suggestions here? Instead of expanding about 1?
8.
Maybe expand about 8. Why 8? Because all my derivatives are going to have a 3, which means all my derivatives are going to ultimately involve cube root. And cube root of 8 is really friendly. So if I was going to do this problem, I would expand it not about 1, but about 8. And the Taylor series is only good if you're evaluating it near where you expanded it about. That's why all of my examples, I was using really, really small numbers in my integrations, because we were expanding those about 0. If I was using larger numbers, we might expand it about some other number. 0 is extremely convenient. So I would do this problem, take all my derivatives, expand them, evaluate them at 8. And then the nature of the problem would be very similar, but instead of x minus 1, these would all look like x minus 8. Because now when I've actually plugged in this case we're using a 1.2. We expanded about 1, so everywhere you see an x minus 1, I'm going to replace x with 1.2. So my actual calculations are 0.2s to powers. In this case, if we expanded about 8, then everywhere you see an x, I'd replace it with 8.1. And therefore, what would you see in calculation? 0.1 to powers all over the place. And that's why that would probably be a really, really good, accurate calculation. So as we follow this one all the way through, I got a bunch of derivatives. I've developed just the third degree Taylor polynomial, meaning I've only gone up to degree 3. That's not very far. Now when I go up to degree 3, okay, that means I'm saying that the cube root function is close enough to that to give us pretty accurate information. Now, how accurate? I don't know. That's what the remainder theorem is for. Now, the remainder theorem can be kind of tedious. The remainder theorem says if I have something that converges, getting small fast, no matter where I stop, I can actually evaluate the next term somewhere, and that would equal all the rest of the terms combined. We called that number z. That number was somewhere in my interval, and so we made what's called an interval estimation. Our calculation of cube root of 1.2, our estimation, if you look at the sheet, was 2,152 over 2,025. It's a rational number to estimate. I can cheat with my calculator to see just how close that is. But now we use the remainder theorem to determine, okay, can you give me an interval estimate? Can you say with certainty that my actual calculation is between point A and point B? And so that's what the remainder is. It says that the next number is smaller than, okay? So my next number is the next derivative evaluated at this mythical magical z, where z is between the number I'm expanding it about, which in this case is 1, and the number I'm calculating, 1.2. So what do I choose for z? I choose the value in that interval from 1 to 1.2, that makes my remainder the absolute largest. In this case, because all the x's derivatives ended up in the bottom, I would want to choose 1, because it's in the denominator. And so when I replace z with 1, I've got an upper limit now on my remainder, which after just a third-degree polynomial is roughly 2 over 30,000. My remainder is smaller than that. It means I missed the mark by less than that amount after just 3 degrees. Now, that doesn't equal my remainder. If it equaled my remainder, I just add it back on and I have my exact value. Now, here's the other thing that throws a lot of people. Those of you who have had statistics, you have an estimation, and then you calculate an error and you do a plus or minus. It's called a confidence interval. In statistics, that's what we do, because we don't know if we're too high or too low with our estimation. But in the Taylor series, we know exactly. Because the terms are getting really small really fast, wherever I stopped, if my next term would have been positive, that means my estimation is too small. If my next term were negative, it means my estimation was too large. So rather than do a plus or minus, I only have to work with one side. If my estimation is too large, then my estimation is the upper limit, and my estimation minus the remainder is the lower limit. If my estimation is too low, then my estimation is the lower limit, and the upper limit is my estimation plus the remainder. So in this example here, what do you notice? In this example here, tell me about my remainder. Oops, wrong one. My remainder involved a negative value, which means my next term would have been negative. So it means my estimation is too big. So my estimation, the 2152 over 2025, is my upper limit. And then that minus my remainder is my lower limit. So when I put everything over a common denominator, I don't know what the actual value of the cube root of 1.2 is, but it's between 32,278 and 32,280 over 30,375. That's a ridiculously narrow margin. Now, if I wanted that margin to be even smaller, what do I do? More terms. Is it a lot of work doing more terms? No. Now, if I program a computer, write a simple do loop, have it do 50, 100,000 terms, you'd have remainders so small that it wouldn't even be worth calculating. You'd have remainders 10 to a ridiculously large negative number kind of stuff. So the benefit of a Taylor series is that I can use a polynomial and a rational number to estimate a transcendental function, an irrational number. And I can predict the degree of accuracy I want. I can decide to make it as close as I want by just simply taking more terms. Okay, we have a way of doing that. I can integrate things that don't have any antiderivatives. In the upper levels of statistics, everything is based on asymptotic convergence. How many have had statistics in here? You know, you're in it right now. In statistics, populations are large. In fact, often we just say, pretend your population is infinite. You're now going to take a sample, which is finite, and use it to make a conclusion about an infinite population. That's kind of dangerous. The larger my sample is, the better I can be. And the upper limit would be if I take a limit as my sample grows without bound, converging on the population. That's not always practical. So we say everything we do in statistics is based on asymptotic convergence, that my sample will converge to the population. Therefore, I can never say it's exactly this, but we give a lot of intervals, say I'm pretty sure it's between here and here. I'd like my intervals to be small. We don't like large intervals. Next year, we predict our company's going to make $1 million, plus or minus 10 million. You know, that would be kind of unsafe. The average height of a Mesa College student is 150 centimeters, plus or minus 300 centimeters. Well, I'm accurate. I think I captured everybody. Right? Some of you are really tall. Some of you have negative height that way. That's not very helpful. What would you rather say? This is my estimation, and my plus or minus is really small. But the only way to control that in statistics is to make your sample size really large. The larger the sample, the narrower the interval, exactly like the Taylor series. That's why all of statistics is actually based on this type of mathematics. We don't teach that in stats because calculus isn't a prerequisite. But if you went on to upper level statistics, you work with Taylor series. Oh yes, you work with Taylor series a lot because what you do is you use the asymptotic nature of the simple polynomial to make estimations about something really, really complicated because it's easier and you know you're going to get tremendous accuracy. Okay? It's kind of cool. That's actually all I have for you today. It's a lot of stuff, and I know this is not the easiest stuff in the world, but if you're in Calc 2, I think it's the most interesting stuff. Unfortunately, you're not going to work with this anymore in the calculus sequence. If you're going on and studying mathematics and you take your upper division mathematics, then you start seeing this, but it's part of a much bigger picture called functional analysis. And functional analysis is the concept that anything you can possibly think of, you can just scribble on a piece of paper. But if that represents a function, then that function has a Taylor polynomial or a Taylor series. And if it has a Taylor polynomial or a Taylor series, then I can do any calculation I want, no matter how nasty the function is. Everything has an answer, in other words, no matter how icky the question, if it's a function. If it's not a function, all bets are off, right? Because I can't take closed form derivatives and things like that. All right, so that's it for today. I appreciate Matthews has videotaped this. I don't know how this is going to work and when people are going to be able to see it, but go ahead and stop that now.